Binomial distribution. We're talking about a binomial. We've talked about the binomial expansion. We've talked about finding a certain term of the binomial expansion. And we found probability. We found a certain term in the binomial expansion without doing the whole expansion. Now we're talking about distribution. Okay, so let's look at this. What is it? It's when a situation, we're doing an experiment, involves repeated trials. Each trial has only two possible outcomes. So like it's either black or white, it's heads or tails, it's males or female, and it's raining or it's not raining. It's something like that. Okay, it's true, it's false. We don't have a middle choice. Only two choices for it to happen. Success or failure is a big thing on this one. The probability of success is constant throughout the trial. So this is what we're talking about in the binomial distribution, is about the successes. So on the first trial of your experiment, the probability of whatever is to happen, the success of it, is the same as happening on the second trial, or the third trial, or the fourth trial. The probability stays constant of the success rate. So if your success rate is 0.4, what's your failure rate? 0.6. So for us to win the CIF, well, this isn't very good. I'm just kind of making fun. The success for us to win CIF boys swimming is 0.9. What's the probability of the failure?
0.1.
Because it has to add up to 1. Very good. So let's look at a problem here. You're going to have two ways of doing this. You're going to learn about tree diagrams and then also figuring it out just algebraically, and I will help you with that. There's a little formula. And it's very similar to the Arth formula, but it has a different twist. There's one little difference, so that's what you have to pay attention to and compare and contrast. As a part of a promotion, a store is giving away scratch-off cards. Prizes are awarded on 40% of the game cards. Suppose you have 3 cards. Find the probability that exactly 2 of the 3 cards will reveal a prize. Each card represents a trial with a probability of success of 0.4. The probability of failure is 0.6. The tree diagram below shows the probability along each path. So here is the first one, my probability, and here you have 0.4. This is saying probability, this is happening, happen. P is yes, N is no, failure. So 0.4, 0.6. Then this broke off for the second trial, 0.4, 0.6. Then this one went 0.4, 0.6. If you go along this whole outside branch of the tree, it's PPP. Okay, it happened. It's success, success, success. Okay, here would be success, success, failure, PPN. Here you go and make another branch. I'm sure you've done these before. You have a success, failure, success. Okay, and you keep going on and on and on. Here is the first trial. Here is the second trial. I guess that stands for prize, right? That you get a prize. First trial, second trial, third trial. Notice in the third trial how many lines you have. You have 8. Why do you think you have 8? 8 possibilities of the third after the 3 trials. It's if you do the blank, 2 times 2 times 2. In your first probability, you have 2 choices, or first trial, you have 2 choices. In the second trial, you have 2 choices. The third trial, you have 2 choices. If I had 4 trials, how many lines would I have at the very end? If I had 4 trials instead of just 3 trials, okay? What would it be? 16. It'd be 2 times 2 times 2 times 2, which is 2 to the 4th, right? If I have 5 trials, you'd have 32. Would not want to make a tree diagram of that. So the probability that exactly 2 of the 3 cards will reveal a prize is 0.288. How did they get that? Well, if you look at this, 2 prizes, 2 of the 3, so I'm looking for 2 P's in each one. Here's one, here's one, I'm going to circle them. Here's one, and here's one. So notice what they did here. Whoa, I almost missed my chair. You have 3. You have 0.4. Why is it 0.4? Why do they have 0.4 here? That is the probability of success. And you have 2, and you have 0.6 to the first. And if you multiply all that together, you get 0.288. Now, how else could have I written this? This could have been the combinations of 4 things I want. No. I want 3 trials, and I want 2 successes. Please pay attention. There were 3 trials. I want 2 successes. My probability, I want 2 successes, and then I'd only have 1 failure. Now, do you see a difference from finding the rth term? What would be the difference here if I would be setting up the rth term here? The 2 should have been here, and this would have been 1. But it would not make any difference of what this number comes out to be. This will still be 3 factorial over 2 factorial, 1 factorial, which would just be 3. But this would be totally different because I have 0.4 squared and 0.6 to the first. If I would have had those in reverse, had this 2 and this 1, I would have gotten a whole different number, right? So this is on a binomial distribution where you're finding the probability of success. You're taking it of, this is the formula, the combination of n things taken x at a time, and it's, sorry, thank you, because it's not on there. It's p to the x, how many times the failure, and q to the n minus x. The binomial probability, what this is talking about, is suppose you have repeated, independent, keyword, trials. Each trial is independent, okay? Each with a probability of success P and a probability of failure, which they label as Q. So therefore, P plus Q should equal 1, okay? So then what this whole thing stands for, then the probability of X successes in N trials, and that's what this is. So, it's an easy formula to remember. If you're trying to find the probability of successes, P is of the successes, Q is this. So P, these two have to be the same. Okay, because this is representing successes. So let's look at this example here. And this is all we're doing. Then you go work on your homework. How about that? A short day. Okay. NASA hopes, it should be hopes, to launch a rocket on one of the next 3 mornings. For each morning, there is a 30% chance of suitable weather. That means that it's good to go. What is the probability that there will be at least one morning with suitable weather? So at least one morning means what? It could be 1 morning, 2 mornings, or 3 mornings. So we have how many days we're talking about? 3. So you're talking about 3, and let's say that all 3 days are suitable. So this would be P to the third, and this would be Q to the 0. Let's say that only 2 of the days are successful or suitable. So then it would be P to the what? 2, and Q to the 1. Because we're taking the number of days and how many days are successful. That's what the binomial distribution is all about. The probability of success. Yay for success. And then we would have 1. So the only one it's missing is 0 mornings. And obviously then it's not flying. So how would I put, this is using the formula. So on here now, how does this all change is, I'm going to put in, where does this 30% chance come in? Where would I put that? It's the percent of what? P, of the success. So the probability of success, but that's not on here. There it is 0.3. So the probability of failure is what? 0.7. Remember we said that they have to, this is P, this is Q. They have to add up to 1. So here you have the combination of 3, 3, and this is 0.3 cubed, Cheryl, and this is 0.70, and I'm going to be adding these. This is a combination of 3 things, 3 mornings, 2 have to be successful, 0.3 squared, and 0.7 to the first. This is 3 mornings we have to choose, and only 1 day is successful. 0.3 to the first and 0.7 squared. This all comes down to what, class? 1. What does this come down to? 3, because it'd be 3 factorial over 2 factorial, 1 factorial. So this is just 3. What does this come down to? 3 factorial, 1 factorial over 2 factorial. That is 3. Because the 2 and the 1 cancels. Okay, so I have 1 here. If I multiply this, I get 0.027. This is times 1, so I have 0.027 for the first term. This would be 0.09 times 0.7, and you would get plus 0.189. This would be times 0.3, and this is 0.49, and you would get plus 0.441. Add them all up, and you would get 0.657. That's the chance of them to launch the rocket. So it's around 65.7%. Your book will probably have this as an answer. Since this was here, you can just leave it as a decimal. Okay, any questions on that? Binomial distribution. If I would have said, if I would have said to find, I don't want to draw on there. If I would have had something like this, P and Q stands for anything, and I would have had to the third power, and I would have said find the second term, what would you do then? How would you set that? Kenya. How would you set that up? Class? It would have been, if I wanted you to find just the second term, Max, listen, to this binomial expansion, I'm not concerned about this is success or failures. How would I set that up? It'd be 3 what? 1. And this would be P and Q. This would be 2 and 1. Now let's go to the fact that I want 3 trials, 2 successes. Now how am I going to set that up? It would be 3 trials, and what would I put here? 2, because this is always represents successes. And then this would have been P to the second, and this would have been Q to the first. So everything kind of stays the same except for this, right? Okay, very good. Okay, now, last thing. I probably spent 10 minutes on doing this because in your homework you have to do it. And there's not really any space on this because it's gigantic. But on your back of your worksheet packet, I want you to make a tree. And I had such a hard time, a tree diagram of this. And let's say that P is suitable and Q is not suitable. Sorry. But and it's good we didn't waste another sheet of paper. And we want to have 3 mornings, and and maybe some of you guys will do this really, really great, but I had a really hard time doing it when I did it. So try and do this, and then we'll talk about it.